Alright, so what I wanted to do was pick up where we left off from Chapter 4 and get a little bit into this digital image processing question that we had raised before about signal-to-noise ratio in images. And first thing I wanted to do was talk a little bit about what it means to see with your eyes. Because when you start to talk about images, you're really talking about the human perception of the electromagnetic spectrum that we are sensitive to, which ranges approximately between 400 nanometers and 800 nanometers in wavelength. When it goes beyond 800 nanometers, that is, when the wavelength gets longer than 800 nanometers, we have a term for the light. What do we call it? Any ideas? What do you call light that goes beyond 800 nanometers, like 900 nanometers? That would be infrared. But if you have light that goes in wavelengths shorter than 400 nanometers, what do you call it? Now you can call it ultraviolet, right? Because what happens when you have a shorter wavelength is you go up in frequency, and when you have a longer wavelength, you go lower in frequency. Now, humans really have a very restricted area of bandwidth between 4 and 800 nanometers. In other words, we have a 400 nanometer bandwidth. Now, it turns out, as a result of this, when you design a display, you design it for humans, which means you're designing it to stimulate the human visual system in a specific range. So when you digitize images for humans using a camera, you typically have it working in the visible light range. However, it is entirely possible for you to modify a camera so that it works outside of the visual range, or to buy a camera that works outside the visual range. And not only that, most cameras today work outside the visual range already. In other words, if you took an iPad and set it up to show what's being displayed in front of its camera, and you flashed an infrared remote, you would see a nice bright light, because the iPad has a CCD element in it which is capable of responding very well, thank you very much, to infrared. So it will see what comes off of a little infrared remote like this. Meanwhile, if I take it and press the button and point it at you guys, you don't see anything, right? You don't see it. You can't see it because your eyes are totally insensitive to the 900 or 1300 nanometer wavelength this is emitting, right? So you can't see this. But the CCD elements in a camera can. So it is the case that we've got very finite range. Now snakes could probably see it, because snakes can see into the infrared. It's part of how they hunt. But we don't design our computer displays for snakes. So color monitors are made for people. And people have eyes, and the eyes have limited sensitivity. They have peak sensitivity at green. They have some sensitivity at blue and some sensitivity at red. And so that's because of dyes that are in the backs of our eyes, our retinas. And so what happens is we can... this is not advancing. I don't know why. Why isn't this advancing? Oh wow, it went all the way to the end. That's weird. Let's go to the beginning. Page down. I hit the end key instead of the page down key. That's typical. So what I'd like to do is talk a little bit about your eye. Your eye it's a machine. Your eye is a machine which takes energy in one form and converts it into another. It takes energy in the electromagnetic spectrum, and it converts it into energy that goes down your optic nerve, electrical energy. Your optic nerve is really a bundle of neurons, about 250,000 of them in your optic nerve. And the rate at which neurons can transmit data is finite. It can go at about 12 hertz. That's it. 12 hertz is your synaptic retention time. So what happens after 12 hertz is different images begin to fuse, and instead of seeing different images with a flicker, they all of a sudden seem like they're moving continuously. Similarly, if you hear individual pulses at 12 hertz, you'll hear them, but at some time, it's different for everybody, but sometime around 13 to 20 hertz, they begin to sound like a tone, a low tone. So instead of being able to hear the individual pulses at 20 hertz, you hear the tone. And so this is because of your synaptic retention time. The ability to focus an image onto the film plane of the eye, which we call the retina, is a function of a lens and the distance of the lens away from the retina. The distance of the lens away from the retina is called the focal length. Muscles in your eye adjust the focal length. You can change the shape of your eye. This is a very interesting thing. You can also change the shape of your lens. The other thing you can control, is you can control the amount of light which is admitted into your eye using what's called the iris. Your iris will narrow down in bright light, and it will get wider in a darker room. And you can actually try this on your own, shining a light into your eye and then removing it. You can see the iris closing and then opening up. Turns out in bright light with a iris that's quite narrow, we'll call it pupils that are narrow, you can reduce the number of different rays that go around what's called the circle of confusion. That is, the constraint of a small pupil keeps the stray rays from going into different places at the end of the ray bundle, which means you can control where the rays go in terms of your retina, and you can bring things into a sharper focus. This is why people say you will ruin your eyes if you read by the light of a candle, because if you read by the light of a candle, you don't have enough light to put things into sharp focus, and so your eyes get strained. So you can suffer a lot of eye strain by using dim light and then try to read, because that circle of confusion for the ray bundle has been increased in its diameter because your pupils have enlarged. Well, computers emit light. So if you have an iPad, for example, and you're reading it in the dark, well, not all computers emit light, right? The Kindle has something that requires light. Right? It's called e-ink. So that for everything I say, there's an exception. But for the case where you have like an iPad that actually emits light, it's okay to be in the dark because it's actually giving you a great deal of energy output. But if it starts to dim and you have to focus and strain, you can cause an eye strain headache. You definitely can strain your eyes with like an iPad mini because it's got these tiny little fonts, but that's a different problem. So the way I think of it is the eye is a camera, and the camera has a lens, and the camera has a film plane, and the camera has a connection to an image processing system. And the image processing system is connected to the camera through an optic nerve, and the image processing system is able to store an entire image in what is known as the geniculate reticulum. In other words, I can close my eyes and still see the room because the entire image has been stored for a brief amount of time in short-term visual memory. The visual cortex in the geniculate reticulum will even allow me to access the image and answer questions about it. In visual communications, the way you measure this is using a device known as a tachistoscope. I don't know if you've ever heard of this, but it will flash an image quickly on the screen, and then you can ask people questions about what they saw. And they are as good at answering those questions as people who study the image for a long period of time. Turns out you can store the entire image in your short-term visual memory and then access it, which is remarkable. So your ability to do what I will call low-level microscopic analysis of what happens inside of the brain is pretty good. Neurologists can do that. In fact, they do these horrendous Dr. Mengele-like experiments by wiring up cat brains and monkey brains and measuring what actually comes off of the visual cortex. In the continuum between the microscopic and the macroscopic, there isn't a good understanding. In other words, emergent properties like consciousness are not explained very well by neurobiologists. However, the ability to stimulate certain areas of the brain with different angled textures, that's something they can measure directly. And so what happens is you have good feature extraction capabilities inside of your brain by using I'll call them a bank of filters. And that filter bank works in parallel. And what it does is it takes the features that come off of the short-term visual memory, and it creates a saliency map, which is a map of areas of interest inside of the brain. And that can be accessed by the cerebellum, and you can think about those features. So in other words, if you're trying to track something that's moving, the brain can be very good at that, especially if you're in the hunter-gatherer mode, which is kind of how we evolved. And so we're able to, in a sense, do certain things that computers have trouble with, like dodge when somebody swings a bat at us, or try and track and kill something that's moving. So we're good at certain things because we're hardwired to do it. So when we think about the camera analog, people say, well, what's the resolution of our eye if it's a camera? And what we're dealing with is a multi-megapixel camera. The eye has a lens with adjustable zoom. It has an iris, a pupil with adjustable automatic f-stop, and it ranges from 2 to 8 millimeters. It has a sensor plane. That's the rods and cones in the retina. It's about 100 million pixels. Think about it. A megapixel image, fat. We don't need that. We got 100 million pixels. That's pretty good. And then we have we'll call it a relatively narrow range over which we can sense electromagnetic radiation. That 400 to 800 nanometers is about the limit. Blu-ray lasers, which you can see, run at about 403 nanometers. Anything out to 380, I don't think you can see. And it is the case that you need a much more powerful laser at 400 nanometers to get the same apparent brightness as a laser that you might see that's green, which would be perhaps 540 nanometers. So then comes the data rate. So you're thinking about resolution. Okay, you could take a single image. How many images per second can you get? Well, you have the synaptic retention time problem, right? You're dealing with 12 hertz synaptic retention time on 250,000 neurons. So take your 12 hertz and multiply it by 250,000 neurons, and all of a sudden you got a mega sample per second, megabit per second quantity, and it looks like it's about as fast as USB 2, half a gigabit per second per eye. And so USB 2, that's doable. I mean, I think even this computer has USB 2. Everybody has USB 2. 480 megabits per second. That's typical. So turns out we're not particularly fast with our processing. As a matter of fact, we might even be no faster than, let's say, a CCD camera. Except there's a question then. But if you've got all those pixels, right? Page up. Someone said 100 million pixels. How are you supposed to squeeze them through, a 250,000 neurons? How does that work? And the answer is, inside of the eye, there are local mechanisms that allow different neurons that are adjacent to one another to be stimulated by several rods and cones. So several rods and cones can stimulate a single neuron. Then comes this next thing about response curves. You know, are we linear? That is to say, if a linear increase in power occurs, will we see this as linearly brighter? And the answer is no. There's an exponential response to brightness, and there's a Gaussian response to light. And so biologically motivated image processing tries to make use of the Gaussian response to light. And in response to that, what I have done is I've created a series of Gaussian filters that essentially do low-pass filters with Gaussian curves. Now, if you think about Gaussian curves, what you're really thinking about is these nice, smooth curves with relatively contained areas and fairly long tails. Right? So these long-tailed Gaussian curves can be modulated by a variety of different things, including sine waves that give them little ripples, and you can orient those Gaussian curves. And the quantization of the image, remember we said there was a finite number of numbers which can be used to represent the signal, even though the signal may have an infinite number of different numbers initially. When you digitize it, you quantize it. So we have a finite signal-to-noise ratio that we have to deal with. And usually we get at about 6 dB per bit. And then you add a 4.8 factor in there. So signal-to-noise ratio is given in log because we have, I would say, exponential decreases in our ability to perceive small changes when we go to high levels. We're far more sensitive to small changes in light at low levels than we are to small changes in light when it's very bright. The other reason you use signal-to-noise ratio, because of its exponential change requirement, is because when you do something like transmit at power, you could have like 10 kilowatts coming out of your transmitter. That's not atypical for an FM transmitter, but the power that you get at the receiver, you're lucky if you can get a few millivolts. So usually you have so many changes in orders of magnitude like that, people work with dB. dB is very good at handling large changes in orders of magnitude, kind of like you might think of as the Richter scale, where if you're in the Richter scale, small numbers like 7 versus 7.8 can be the difference between a building that stays up and a building that falls down. I think the largest earthquake anyone has ever seen in human recorded history is like a 9. Right? So, 6 might be very common. 9 maybe has happened perhaps once or twice. I think in Japan they had a 9. So here's that signal-to-noise ratio again. And now comes this interesting thing. If you have a specific image, like the image of my knee, and you're looking for signal-to-noise ratio, and you identify, perhaps because you're enough of an expert to know what the background looks like versus the foreground, you can isolate that background, measure the background, and say that's how we characterize our noise. And then you can isolate the foreground, measure the foreground, and say, aha, that's how we isolate and identify our signal. And so then the big question becomes, what is it we're going to do to identify the signal so that it is inherently different than the noise? How do we statistically identify the signal? Well, I like to think of something like the signal-to-noise ratio being identified by the signal area, which is quite well known for the sensor and perhaps the particular image, and the noise area, which is quite well known and easy to identify. Right? So if I can take that image that we saw initially, and I don't like to work with the JPEG image because it is a lossy image. I'd rather work with the DICOM image, so I may go back to ImageJ. I'd like to isolate the noisy part and try and just characterize that. All right, so that noisy part, that's that background. And the signal part, well, that must be the foreground. And there must be something statistically different between the background and the foreground. And so maybe one of the things I can do is I can look at something as elementary as the standard deviation. So do you guys know how to compute the standard deviation? Yes, that's exactly right. That's right. The square root of the differences between x squared, that is where x is the sample, and I'll call it x bar squared, where x bar is the average. So the difference of the sample versus its average, and you can sum up all of the differences and take the square root, and that's your standard deviation. Square root of the variance. Yes, that's exactly right. Square root of the variance. Yeah, if I say, well, it's just the square root of the variance, and you say, okay, yeah, well, okay, what's the variance? Yeah, that's exactly what it is. The square root of the variance. So it shouldn't be too hard for us to take a little sample of a two-dimensional array and come up with the square root of the variance. And in fact, here's a very poorly rendered thing. I tried to paste it in here instead of rendering it using, let's see if I can do this. I know how to do this. Excuse me here. Go in here, run, got this program, can open up an image, open, here's the image, open. So what would happen if we tried to take the image and crop it? So to crop it, what I would do is, I guess I could reduce the height, and I can reduce the width. There you go. So that must be the section of the image that contains some background. I can reduce the X part, but I don't want to go too far. I can reduce the Y part. I can apply my change, and now I can save as, I guess I'll save it as JPEG, I suppose. JPEG, and I'll give it a name, and let's call it I don't know, I was going to call it noise. How about this? Noise. That's fair enough. And then I would like to do sort of a similar thing to the knee itself. Let's open it up. JPEG, open. And I'd like to identify the knee, well, let's say the signal, not the knee, just the signal. So let's identify the signal. So what we'll do is we'll crop the image again, only this time with a difference. And the difference is we'll slide the image over. Oh, don't go too far. So then we'll reduce the width somewhat. Going over here. Then we'll try and reduce the height somewhat. That's sort of looking like signal. That is the look and feel of muscle or whatever the heck that was imaging. So now we'll apply that, and then what we'll do is we'll save it as a JPEG, and we'll call it knee signal. So this is a real biomedical image. and we'll save it. And now I think maybe if I were to use other tools, I would still be able to image it because it should be compatible with the tools that Windows has available for me. So in theory, I should be able to go into my data directory, if I could find it. Here it is. Go into Images, and here's something called knee signal. You know, I should have done is I should have given it a .jpg suffix. And then what we'll do is we'll do that again, only this time we'll do it for the signal. We'll give it a .jpg suffix. Okay. So now I've got three images. I've got the original image converted to a JPEG. I've got the knee signal, and I've got the knee noise. And what we'll do is we'll take this original image and we'll give it the name knee. So now I've got three images: knee, knee noise, and knee signal. And if I open this, what happens? Oh, you can see it. That looks like the knee. Uh-oh. Knee noise didn't change anything, and knee signal didn't change anything. So something happened here. Perhaps my idea of how to use my program was not correct. So I've got to go into the knee noise and isolate the noisy part, and go into the knee signal and isolate the noisy part. Isn't there a nice program for doing that, like Paint or something? How do you open this with Paint? I go to Properties and change that. There should be a Paint program. Yeah, here it is. Okay, Paint can open. Yeah. So I'll just I'll select, this is supposed to be knee noise, so I'll select the noisy bit. I'll cut it, and then if I say new, does that make new from
You can make a new file and then paste it.
how do you do that?
Paint. You have new.
Paste. Now can I save? Save as JPEG. Oh, now he makes me navigate all the way back to Data, Images, and we'll call this noise knee noise 2 or something, I guess. Knee KNEE noise 2. There. Save. So there's the noise, and now I got to do it again for the signal. So we'll just grab a chunk. Oops. Is there like an undo on this? You can see that? Where's this home?
Control C.
Right above where it says home, it's an arrow.
Oh, is that what that is? Yeah, you can tell I'm not a Windows user. So I'm thinking there's like a way to select the signal, and then I guess I have to cut it and then say new, and then I don't save, and then I paste, and now I can save it, I suppose. Is that what this does? Yes. And so now I'll call it signal JPEG. KNEE signal 2. Enter. Now, what's the size of this image? It looks to me like all the white part in here is being used as a background, but I'd like to crop the image to just the area of interest. So I have a feeling that there's something about this image that I'm not quite understanding. What if I said crop? Can that work? Yes. That's what I wanted. So now I should be able to save it. And that worked. And then if I go over in here, oh, guess I could have done that to begin with. Here's knee signal. I could have just here we go. Just take the part you want and then go in here and you can do a crop. Perfect. And then save it and you're there. So knee signal is good. We can cut that. Now, delete it. Yes. Noise we can delete. Now here's the noise. We'll just isolate. I did it again. Shoot. Some people live and learn and other people just live. Okay, so we isolate the noise and then we go into the image and we do a crop and then we do a save and that's it. So now I got the knee. I got the noise. And I got the signal. How's that? Good, right? So now what I can do is I can take the knee, the noise, and the signal, and I can upload them, and I can have you guys isolate the noise from the knee using the noise and using the knee, the noise, and the signal. And the question then becomes, how would you do that? How would you identify the signal to noise, the signal and the noise as separate entities? Any ideas? We had this thing about standard deviation, right? So if each pixel is treated as a event, right, where the event comes in, we should be able to compute the average, right? The average pixel value. That sounds like something you could do, right?
Yeah, so if it deviates, so you would have to set like a threshold. So if it deviates X amount from the average, then you would say that it's not good, discard it.
Yeah, let's see if we can open these images that I just saved, just for, completeness. I'm going to use my little image processing program. I'm going to open up my my noisy knee image. Maybe I should open up the signal first. Let's open up the signal so we can make sure we've got something. And that kind of looks like what we saved. So that looks about right. So now, what do we got here in terms of data? What does this data on filters mean? What does that do? Very interesting. So we've got stuff. I've got RGB average. I've got signal power. I've got standard deviation 12.6. That's nice. Look, I got the 12. It's the same for red, green, and blue because it's a grayscale image. What do we know about grayscale images? In image processing, for people, images have red, green, and blue. And if it's a grayscale image, the value of the red, green, and blue pixel are all the same. So they should have the same averages. They should have the same standard deviations for the red, green, and blue color planes. Because it's not a color image, it's a grayscale image. Well, you could say it's monochrome, if you will. But in fact, there are 256 different possible levels of gray. And it says here there's only about 8,000 pixels. This is not a very big amount of data to process. Now there's this other image in here. We're calling it noise. Okay. Looks kind of black, but maybe there's something there. Let's go to the data on this. And now when we look at it, we see, aha! It's got the same standard deviation as the other thing. Oh no, it's a little different. The average, the RGB average here is 12.2. The RGB average there is 64. RGB standard deviation here is 1.5. RGB standard deviation here is 12.6.
12.6, 1.5, 1. It's like, what's the unit of the...
Well, you gotta think about it as the quantums that are available to you as in the pixel. So these are 1.5 quantums. So the pixel energy is represented by a number that goes from 0 to 255. And within that range, if you see a standard deviation of 1.5, then you could perhaps safely classify that area as noise. But if you saw the standard deviation of the number going to 12.6, you could say, aha, I'll classify the area as signal. I mean, one thing I can tell you is the signal appears to be generally brighter than the noise. But not only that, the signal appears to have, in general, a higher standard deviation than the noise. So when we look at the segments of the image that are classified as signal versus those that are classified as noise, there are statistical properties which can help us with that classification.
It could work the other way too, then.
It's possible that there are no statistical differences between signal and noise.
Well, couldn't the noise be over exposed? Like noise from overexposure. And then in that case, it wouldn't be higher.
Yeah, the pathological adversary can say, oh, Professor Lyon, what you're proposing will not generally be true. But here, for this particular image, it seems to be correct. Now, one thing I can do is I can expose to you the actual noise in this image by doing a histogram equalization. And now, when you look at it, you can see that standard deviation is really making a measurement of texture. And you can see that texture right in here. So you've extracted what I would call a feature. Right? Standard deviation of the intensity of the image is a feature. A feature is a summative measurement of something of interest. And whether or not you have selected a good feature will determine whether or not your pattern recognition program will be effective. So maybe texture features aren't good. Maybe you should be looking at lineal features. But in this particular case, because we're dealing with what I would call a fairly well-behaved noise, evenly distributed across the image, looking like a texture, standard deviation, by my heuristic, by my experience, isn't a bad feature to start with. Whether or not it's the one you want to end up with is another matter. Nobody in computer vision has any analytic closed-form guidance for you to determine what good features will be. That is an art. That is the part of image processing that you really have to kind of get a feel for and get good at on your own. So if your goal is to find the difference between, let's say, grass and tarmac and or sky, because you're trying to segment an image, well, the features you select may include texture features, they may include lineal features, they may include color features, they may include other kinds of features. You, in fact, have to be very domain specific in terms of what features it is you want to select in order to be able to segment an image into large areas. And it is your knowledge about that image and the kinds of image you plan to encounter that may make a difference. For example, I worked for the Rome Air Force Development Center doing long-term Landsat photo reconnaissance. The goal was to try and find over-the-horizon ballistic missiles. They had an infrared image sequence coming in. That's a very specific domain image. Doing that kind of image recognition inside of the satellite, it might be a lot easier if you know exactly what you're looking for in terms of a contrail or in terms of a booster phase for some kind of a ballistic missile. If your goal, on the other hand, is to find tanks hidden under camouflage, in some forested area, you may use a completely different approach for your target identification. When the British were looking at pictures of the Nazis during their long-term photo reconnaissance, which was not based in satellite, they were using airplanes, they had no idea what they were looking at when they were looking at Peenemünde. They didn't know what a V-2 launch platform looked like. They just saw these long areas and said, we don't know what this is, and they went on and looked at other things, like ball bearing factories to bomb. They had no idea that they were supposed to be bombing V-2 rockets. They didn't know what they looked like. Then later, when people said, I think this is what these guys are doing, did you see anything that looked like this? And then people said, yeah, is that what that was? And they finally went back and they were able to bomb it. So kind of knowing what you're looking for, that's very critical. Let's go to this knee picture now, and let's see if the texture looks somewhat different. And yes, it does. Now you could say, is texture a good way to identify noise? Well, let's compare noise with signal. And you say, hey, wait a minute. The signal has very slowly changing energy functions, whereas the noise is very fast changing energy functions. So looking for texture and segmenting on texture, that seems to be a reasonable thing to do. And I'm just guessing that that is going to work. But I do it at least in part by looking at it after a histogram equalization. Now I can look at it and I can say, gee, I wonder if the histogram looks different on this. And I bet you it does. So let's look at the histogram after we apply the change. So we'll apply the change here. Then we'll apply the change over in here. So that actually puts it into a separate buffer inside of the program. And then when we show and register the histogram on the knee, it might look somewhat different than the one we see on the noise. And sure enough, it is. The number of different levels in a noisy image is quite a bit different than the number of different levels in a how do you call it? A signal image. Signal images in general over an area seem to have a lot more different levels. Of course, that's a function of how big the window is too. So you may in fact say, changing the window size when you do the standard deviation measure is going to actually change the absolute function. But I say that there will be a threshold for the standard deviation in general. And you can use a relatively small window, perhaps a 10 by 10 or even a 100 by 100 if you have some overlap, and use that to segment your image. Where segmenting the image means identifying the area of the image that's, let's say, different from some other area of the image, like taking the region of noise and separating it out from the region of signal. Isn't that interesting? And the computations have already been done. But now the question becomes, how would you do this programmatically so it was able to segment foreground from background using, let's say, a simple slider based on the threshold for a standard deviation? Well, thresholding is one of those things that you can do on an image. Right? Thresholding is typically done based on intensity. So let's think about this. If we open up our knee, my knee, open up my knee, right? And then we do a little process here which I will call thresholding. Can I do thresholding? Color, there really should be an easier way to do this. Contrast panel, color quantization. It is a kind of filter, but I would have thought it was under edge detection, maybe. Thresh. Do you see thresh? Yes. Is it up? Left. Oh, left. Thank you. Threshold panel. That sounds pretty good. So what does that do? That uses a number that ranges from 0 to 255. And isolates out everything else. Oh, wow. Looks like threshold's a great way to get rid of the noise. but it's also getting rid of some of the signal. Anything below, see some of the noise is coming in. Anything below a, if this is 63, that's 32. That must be 5, 10, 15, 10, 20. That must be anything below 20. Anything below a 20 in terms of absolute value is beginning to look like noise, but of course there's going to be sections of the image and signal itself that'll be removed. What if we use something like this slider, but we use it for standard deviation, and then have the standard deviation be something like a window that moves across the image? Right? We can compute standard deviation for any given window. What do you think of that? A window that moves across the image. What does that look like in terms of code? Any idea? Right? I want a window, an area of pixels. I want to compute the standard deviation in that area. Then I want to take the window and I want to move it, and I want to compute the standard deviation of that area. So the window could be like a 10 by 10 window, and so maybe I'll have a doubly nested for loop that goes for x equals 1 to 10, and then y equals 1 to 10, and I can do all the pixels, and then I can take the start point. Instead of x equals 1, I can have x equal, let's say, 5, and it'll go from 5 to 15. And then y won't start at 1, it'll start at 5 again, and then it'll go from 5 to 15. So that'll move the window across the image. So the little 10 by 10 window is going to be nested inside of another for loop. So what we're thinking about is a quadruply nested for loop in order to be able to iterate a window across the entire image. I wonder if we can look at the knee again, only this time it's almost as though we wanted to impose a grid and then examine each area of the grid one at a time. So if I said I'm sort of thinking out loud. I'm thinking there's a grid in here somewhere, but I'm not finding it easily. Sometimes it's hard to find all the different features in this program because they're so buried in this hierarchic menu system. I'm not seeing the grid. I may just have to write it myself. That's not too bad. We can do something like that. Let's start by having this sort of conceptual discussion about how we would write this program. So we'll start off with insert new slide. And so what we'll do is let's do the analysis with a traveling window. So we'll do traveling window analysis. So the goal, and I don't think this is such a bad idea, we'll write a program that uses a n by n window to compute the standard deviation and print the standard deviation. The n by n window is smaller than the image. that's fair enough. Move the n by n window around the image in scan line order. Do you guys understand what scan line order is? That's left to right, top to bottom. So now, if you think about it, I can do the simple example.
When you say left to right, top to bottom, you mean whole line and then start at the beginning of the next line and go again? Or do you want
Row
some
nature,
order?
like, is that what you mean?
Left to right, top to bottom means you start at the upper left corner, call it 0, 0,
Right.
and then work your way to the lower right, call it width, height.
What I'm saying is, when you get to the end of the line,
Mm-hmm.
do you start at the left side
Yeah.
of the next line, or do you just go down and
Yeah,
back towards the left?
it means you go from left to right, and then you go back to the left, and then you go left to right again after having incremented your distance away from the top. So you could use an example here, a 10 by 10 window on a 320 by 240 image. Okay. The 10 by 10 window, maybe I should have picked a square image just to be clear. Let's pick round numbers. I like that. On a 100 by 100 image. So then the question is, how many measurements will you get if you have a 10 by 10 window on a 100 by 100 image? Well, it'll go across. You'll have 10 measurements as you go from left to right. And then the question becomes, how will you increment the window? Will you go down just one line, or will you go down 10 lines? So if you go across 10 pixels at a time and then move the whole window with no overlap, another 10 pixels, and then measure the 10 by 10 image, it makes sense that when you go down from the top, you're going to move with no overlap and move a whole 10 pixels down. So if you have 10 numbers going across, you probably have by 10 numbers going down, which means you'll have 10 by 10 or perhaps 100 numbers total. So 10 by 10 window on a 100 by 100 image will take 1,000 pixels and convert it into 100 numbers. Will, with no overlap, give 100 numbers. Alright, that's fair. And in fact, if you think about it, if it was a 20 by 20 window on a 100 by 100 image, what it would really do is it would give us 5 numbers going across and 5 numbers going down and give us only 25 numbers. Right? That's fair. And so what you've done is, you've greatly reduced the number of numbers that you have to do an analysis on if you start with a relatively large window. You could do this with a 50 by 50 window, and that's very nice, because look, a 50 by 50 window, you'll have 50 pixels. It'll give by 50 pixels gives you one number. You move it across. Now you're done, and you move it down 50 pixels. So basically, you're going to have 4 numbers total, and hopefully those numbers will look really different as they go across the image and move towards signal. And as you change the window size, things will increase in terms of the number of numbers that you see, but you'll also increase the precision at which you can segment the image. What do you think of that? So it's a sensible sort of image. I'll call it, is it image processing? I guess so. Is it pattern recognition? Yes. Why? Because you're making a decision, but really you'll only be making a decision if you decide to do something with the information that you extract. Like, for example, zero out the stuff that has relatively low standard deviation and keep the stuff that has relatively high standard deviation. But maybe our first pass through, what we really want to do is have a relatively coarse window That is a large window. And just see what those numbers look like as they come through. That sort of makes sense, right? Could I write a program that does this relatively quickly? Let's do something about that. Let's see what we could do about writing a program that does that. So I'm going to start off by asking a basic question. Do you guys know how to open up an image and display it?
Like in Java?
Yeah. We kind of did this, right? I think a little bit. Yeah, image utils.display image. Right. That's exactly right. I'm thinking I'm going to do this as a homework assignment, and I'm going to get you guys started. And I think the way to do that is to write a program that I can send out in Blackboard. And so what I'll do is I'll just make up a new little Java class, and I give this a homework assignment a number, but I don't know what it is. What number is it? Is it?
I can check. What are you storing it in?
I'm storing it in a file.
Like what folder?
I don't know yet.
Oh, okay. Sorry.
I do not know. So let's just call this standard deviation. But I want it windowed, so I'll call it windowed standard deviation. Was there a homework due today?
No.
No. So for windowed standard deviation, we'll start by opening up an image. And what I'll do here is I'll say something like this. SVM Control-J enter, image utils dot display image, and then what we'll do is we'll say Alt enter so it stops complaining. And now this thing needs some sort of an image, so we'll say image utils dot get image, and then we'll give it a name and we'll call it knee. And I'm thinking I can introduce a variable in here using refactor. So let's extract a variable. We'll call it image. And I can inline this thing, so we'll do another refactor. We'll inline this invocation, keep the method. Now I've got a file. Now what I'm going to do is I'm going to print out the file because I don't want to have to keep navigating through. And when I go to get this image, it'll print it out to the console, and then I'll be able to paste it straight into my program. So here's my knee. I open it up. Here's the absolute path name. I'll copy it, close it out, and now instead of calling get image file, which you'll probably have to do on your own, I'll just say paste, and I guess I have to say new file, and now I've got a way to make this program work without having to bring up a file dialog box, which always slows me down anyway, so I don't like doing that. So now when I run, this should just work. And it does. And so now I've got to write the program that's going to iterate through the image and give me some kind of statistical information. So first thing I'd like to do is I'd like to check my toolkit, image utils, and see if there's anything in here, like for example get average. Oh look, it says get average image from camera. I wonder what that means. Oh, that's going to average the image. I don't want that. So what else can I do? Can I get image utils to give me a two-dimensional array? It can give me the pels, the pixels. That sounds good. What else can it get? What else can I get? Get a buffered image. Get a full screen. An image is an AWT image, and it is generally packed pixels, and a buffered image, they're generally unpacked pixels. Also, the AWT treats an image differently than it treats a buffered image. Buffered images are stored entirely in memory, whereas images can be rendered gradually. on the display. So I can have a separate. I mean, it's a very good question. I can have a whole separate lecture on just that. It's not a particularly easy lecture to have, especially now that we're at the end of the class. You know what I'm going to do is I'm going to make a short image bean, SIB, equals new short image bean. And what I'm going to do here, Alt-Enter, so it stops moaning at me, is pass an image in. And now the short image bean is going to get me two-dimensional arrays of things like red, green, and blue. And I really only care about one color plane. So I should be able to say something like SIB dot get red. And that gives me a two-dimensional array of short. I can also get the average. I can get the standard deviation. How about that?
So we don't
That's
have to write our own method to calculate.
well, you can you know, this is the whole image. It's not a window. But yeah, that's right. You can look at how it was done. So we'll get the standard deviation. We'll get the average on red. What shall we call it? That's a float, isn't it? Or a double, I forget. It's a double. So what we'll do is we'll call it R bar, double R bar, equals. And now what we'll do is we'll get the standard deviation, double R SD equals SIB dot get standard deviation of R. Oh, that's so cool. It's already there. It's already there. Then we'll print it out. Oh, I know. Quote R bar equals end quote plus R bar. That's fair. And then we'll do it again. S out, Control J, enter. Quote RSD for standard deviation equals end quote plus RSD and parens M. And now I think maybe you're ready for this. Can't see it. There it is. So now I've got the entire image. I've got the average red value. I've got the standard deviation for the entire image. And we can see these are very different than the standard deviation that we saw before when we were doing it for just a small area like the noise, or just another small area like the signal. So these are quite a bit different. Moreover, if we look at the implementation for the average, it should be relatively easily understood. And so what I did in here was I called this mat2 get average of the two-dimensional array, where mat2 get average takes all the elements in the array, adds them up, and divides through by the number of elements. That's how you get an average. So get sum on a two-dimensional array is a thing that just adds up all the pixels. And then if I add up all the pixels and divide through by the number of pixels, that must be the average. I'm thinking, because how else would you do that? And then for getting the standard deviation, I use the mat2 get standard deviation. And what that does is, look, somebody said it's the square root of the variance. And look what I do. I call math.square root and call get variance. So now getting the variance says first thing you do is you get the average, and we know now how to do that. We add up all the pixels and divide through by the number of pixels, and then call that x bar. And then for the deviation from x bar, we go through each one of the elements and get that difference. And then we form the sum of the differences squared, right? Sum of the square differences. And then at the end of the day, we divide through by n, and that gives us our variance. So it's x minus x bar squared, add them all up, divide through by n, and then at the end of the day you're going to have to take, well, you actually in this case I think you're dividing through by n squared, and then why is it n squared? Oh, because the total number of elements is equal to, since it's a width by height thing, right? You have the total number of elements is width times height, so that's actually n. So you're really dividing through by n when you divide through by width times height, because the total number of pixels in a 640 by 480 image is 640 times 480. That kind of makes sense, right? Did I go too fast on that? That makes sense, Kevin? Yeah, okay. So standard deviation is relatively simple to compute, straightforward. There's even some handy-dandy routines in MAT2 which handle two-dimensional arrays and do the computations for things like variance and average. But then what you need to do is give it the right two-dimensional arrays, right? So how do you extract a two-dimensional array from a big two-dimensional array, a little two-dimensional array from a big two-dimensional array? And the answer is, well, you got to write your windowed standard deviation to work with a two-dimensional array that's large. So we can get that. I can say something like this. Integer red is a two-dimensional array which equals SIB dot get red. Oh, you know what? It's got to be short. There. So now I've got the ability to print out the size of this image. I can say something like this. Sout Control J enter, quote r dot width equals end quote plus r dot length plus quote space r dot height equals end quote plus r of 0 dot dot length dot length. And so now I can print out the width and height. And he tells me it is a 320 by 320 image. That's pretty cool.
So to make the window, would you have the two outer for loops being the width and height, and then two inner ones being the size, dimensions of the bottom?
Sure. So if you told me I gotta create a window, how am I doing on time? I'm out of time. Window W is going to be, let's pick a number, 32, because it's 320, and it'll go in 10 times, so then 10 by 10, I should have 100 numbers. I could make it 64, and then it'll be 5 by 5, that's 25 numbers. Let's pick it 32, new short of 32 by 32, so that's my window size. So now I can fill up this window with the first 32 pixels using a two-dimensional array for the window. I can say for integer, I need a parenthesis, integer x equals 0 while x is less than w dot length x plus plus, and then I can say for integer y equals 0 while y is less than w of 0 dot length y plus plus, but did we really want to use w? No, we wanted to use, oh yeah, it's the window, that's fine, n paren, and now I can say w of x and y is equal to, and now I can directly access r of x and y, and that fills up my little window. And now I can take my little window W and compute the standard deviation using MAT2. So now I've got a double precision number coming. I spelled my name, double, D-O-U-D-O-U-B-L-E, double precision number, which we will use for WSD, and we'll set it equal to MAT2 dot get standard deviation of... Oh, look, it takes a short. That is fortunate. And so now I've got the standard...
In the loop, or not?
No, the loop populated the window. Now I want the standard deviation of what's in the window. And so I'll print it out. And so now I can say, quote, WSD equals, end quote, plus WSD. And now I have printed the standard deviation of my first window. And there it is. That's a 32 by 32 window in the upper left corner. Now I have to move the window across the image. Now the start point for X and Y, we'll call that X1 or XS, and YS. The end point will be equal to XS plus the width and YS plus the height. And now XS and YS have to be incremented in hops. So what we'll do is we'll have another doubly nested for loop. And this is where things get interesting. This is why I said we're going to have a quadruply nested for loop for integer XS equals 0, while XS is less than, now it's not W dot length, it's going to be R dot length. And now the increment's not going to be plus plus, it's going to be XS equals XS plus, what is it going to be? 32, right? That'll move it over by a whole 32 pixels. And then you need another for loop for integer YS equals 0, while YS is less than R of 0 dot length. YS equals YS plus 32. Now I should be able to now you can see the beauty and elegance of the quadruply nested for loop. Behold the beauty and elegance of the quadruply nested for loops. Yes, sir.
You want to go across first and then down, right?
Yeah. Well, that's what I'm doing.
Why wouldn't you flip this?
That's the opposite way.
That's what they
I got it backwards?
go
Yeah,
Y
I think so.
first and then X, right?
Because you're iterating the...
I did it wrong. I did it backwards. Well, that's okay. I don't have to worry about doing it backwards because I have students. And they can fix it because I'm not going to finish your homework for you. And something tells me that there's got to be another parenthesis in here somewheres. There you go. And where do you suppose we should do the computations? Probably every time we're done with the first two for loops. Right? So these two right in here, that's where you want to do your computation on the window. And then you're going to go through and reinitialize the window with new values. So unless I got it wrong, you tell me. Keep me honest. So I'm thinking there's something to be said for running this, because who the heck knows if that's right, right? Oh, out of bounds exception at runtime. Maybe 32 wasn't correct. How about 31? Because 0. We start at 0, right?
Oh,
Yeah. This is why you should never believe what the professor says. Always question everything. Ooh, look at that. More out-of-bounds exceptions at runtime. So I think you guys can fix this now. That's my cop-out. I'm out of time. Otherwise, I'm going to keep you guys here. But at some point, I got you started, and I think you guys can finish it. And this will give you a good sense for how you can go and do a traveling window analysis on an image. Well, you got to fix the bugs. There's runtime junk. That's, it's throwing array out of bounds exception at runtime. A couple of ways you can do it. You could make sure that you're not incrementing at the end of the array by guarding the input. You could say if x is in bounds and y is in bounds.
So you want us to fix the bugs and then do?
Yeah, you know what it is? I think it's this. These indices are not correct because these indices. Oh, wait a minute. Did I do that right? I gotta. You know what you want to do is you want to go through this real slowly. I was very fast when I wrote it first time through. Go through, put on your thinking hat, and make sure you know what the ranges are on x and y, whether or not the increments are correct. You may find that my code is not to your liking, and if you want to redo it, that's fine. What I'll do is I'll send out the code, and I'll let you guys do the fix. So I'll just write this up as a Blackboard copy. And no, I want you to just print out. I want you to show me your sample. Just do a red. You don't need to do all three colors. Yeah, I want you to print the standard deviations. So let's go through and write this up so that you guys can see it. And we're in biomedical imaging, and we're going to create ourselves a little course content, and we're going to have, I think it's going to be called homework number 4. How exciting. So we got a 4th homework here, and we can make it an assignment, and the assignment is called homework 4 traveling window analysis. And what we'll do is finish the following code example given in class. Show your standard deviation output. Use the knee image attached. And I can attach that. What we'll do is we'll paste in the code, and then we'll attach the file, and we'll browse into the data directory, go into images. Here's the JPEG knee. Give it 100 points. Make it available. Make it due next week at the beginning of class, just 5 p.m. And then all the students. Anything else I need to do here? I think that's it, right? You got the knee. Allow unlimited attempts. Thank you. And submit. And that looks like a homework with sample code for you guys to look at. What do you think of that? Good, right?
Yeah, I think so.
Okay.
We'll find out.
So you will have a runtime when you go to compile this, a runtime error, and you're going to need to modify the location of this file here, because obviously it's local to my hard drive, and you're going to want to uncomment the part where I did a feudal.getRead file, so it'll give you a proper image location. You'll paste in the image location, then you can start to work on it like I've been.
Just, like, have it ask us the location?
Absolutely,
So
but if you do it every time, you're going to end up slowing you down.
Okay.
Like it slowed me down, so I just said, look,
Okay. Because then just like when we upload it, it'll be easier for you to...
Okay, that's fair enough.
Because then
That's
it'll be more transferable.
good point. So you can, hard code the location of the image when you're doing development, but when you're ready to send it to me, you might want to make it prompt for an image location. That's a good idea. So everybody understands the problem?
Yep.
Yep? Kevin? Good?
Yep.
Okay, great. Thank you. Have a good evening. Drive safe.